All right, we'll get started. So, good day, everyone. My name is Riley Edwards, and I'd like to welcome everyone to today's virtual William W. Hay Railroad Engineering Seminar. Before I introduce our speaker today, I'd like to take care of a couple of housekeeping items. First of all, if you have questions, please use our Q&A feature in Zoom at the bottom down there and not the chat feature. So use the Q&A feature for questions. I'll moderate as many of these questions as possible at the end of today's presentation. PDH credits, they're available to our seminar participants. To obtain them, follow the prompts that you saw after you registered, or feel free to send us an email at heyseminar@illinois.edu if you have any questions. The William W. Hay Railroad Seminar Series is sponsored by the Rail Transportation and Engineering Center here at the University of Illinois at Urbana-Champaign. On behalf of all of us, we want to thank the AAR, BNSF, CN, Hanson Professional Services, and the National University Rail Center of Excellence for their ongoing support of rail tech. Their support is greatly appreciated by all of us here on campus and in the virtual world. Today, I'd like to welcome our more than 200 registrants for the seminar, hailing from 12 countries on 6 continents. Again, please ask your friends in Antarctica to consider joining next time. But we've got great coverage throughout the world, and I think that speaks highly to the topic that Dr. Tang will be talking about today. Our attendees include freight and passenger railroads, transit organizations, DOTs, engineering firms, research organizations, technology developers, and others. We're very pleased that we have this great, strong attendance for today, and I think you're going to enjoy the topic that we have. Now I'm very excited to introduce our speaker and the topic of today's seminar. I'll first start with the abstract for today's talk. Railway systems have long served as the backbone of regional and national transport, enabling the movement of people and goods while shaping communities and economies. Today, these systems are evolving rapidly with advances in sensing technologies, digitalization, and multi-scale computing at a remarkable speed. Today's seminar will introduce 3 cases demonstrating key AI advancements enabled by multi-data fusion and high-fidelity machine learning frameworks grounded in real-world deployments. The advancements discussed today will include agent-based learning for urban rail transit, infrastructure multi-sensing for rail track, and condemnable failure predictions for wheel sets. The research that's led by our presenter today also proposes scalable data governance and computing pipelines designed to operate efficiently under extreme data volumes typical of our modern rail systems. Today's seminar will also highlight how AI-enabled approaches can be embedded into multi-scale operations. And our speaker will talk about data and computing challenges and workable innovations to tackle some of these challenges. Now it's my great honor to introduce our speaker today, Dr. Kelly Tang. Dr. Tang is the 2026 chair of the Railway Applications section at Informs. She leads the Mobility Technology Research Group, where she focuses on advancing human network operations and AI in resilient systems and transportation. Dr. Tang is a jointly appointed assistant professor at Western University in London, Ontario, and she has over 50 publications, including award-winning papers in renowned journals and over $5 million in grant funding. Dr. Tang has supervised over 40 PhD, master's, and bachelor's students and engineers, and her group's research outcomes have been widely adopted by industrial partnerships in municipal, energy, and transportation sectors. Dr. Tang has been awarded as a Dresden Fellow at TU Dresden in Germany and is an affiliate member of the Center for Multi-Hazard Risk and Resilience, the Institute for Earth and Space Exploration at Western, and the Center for Smart Infrastructure at UC Berkeley. I'll now turn our event over to Dr. Kelly Tang, who will present today's seminar titled Smart Railway and AI, Challenges, Opportunities, and Innovations at Multi-Scales. So welcome, Kelly. We're excited about your seminar.
Thank you for the introduction, Dr. Edwards. It is my great honor that you have the opportunity to present our studies that in the William Hay Railroad Engineering Seminar at Illinois. So as Dr. Edwards has introducing, today I'd like to introduce some of our studies that addressing the AI, the data, including the challenges, opportunities, and innovations that we have been studying in the past years. So I will first introducing an overview of how the data and AI analytics that has been conducted in the railway system, and we'll introduce three of the case studies that we have been working on, and that has also been collaborating with industries as well as partners to deploy those method and as well as the system that we developed here. At the end, that I will introduce the strategies and what could be the possible solutions for some of the challenges, and also happy to discuss with the audience and hear more feedbacks on this perspective. So railway system is typically operated on the track that in a dedicated right of way. Depending on how the railway system is integrated in the other transportation system, it can be either as independent system. A lot of like freight rail is more like independent system or integrated system like urban rail transit that to be part of the urban mobility systems. So the data infrastructure in the railway system has already been deployed and actually implemented for a decades. And with the continuous collection of the data, reliable data governance, scalable computing, and practical integration, that is, through our experience, we find are the three most critical perspectives towards the AI eras and towards the utilization of the data. And at the end of the day, the key purpose that we are collecting and developing this data infrastructure is to derive what could be the actionable insights that can help improve our demand satisfaction or user satisfaction, to help to maximize our operational performances as well as infrastructure investment through the early stage to the end of the maintenance. So this seminar that I will present three cases that addressing how we could use the data to provide inferences in the railway system, where I will use a case from the urban rail transit. And the second is what could be the prediction methodology and strategies when we are leveraging a multi-sensing data with a case study that how we monitoring the rail track infrastructure. And at the end that I will provide and introduce a case where that we are using the wheelset data set to estimate what could be the failure prediction of the wheels. So the first case that I would like to introduce is when we are leveraging a multi-records, multi-source of the data from the urban rail transit. And the rationale that we drive from here is in a variety of the countries and also metropolitan areas, like especially those transit-oriented regions, like in Hong Kong, Toronto, Montreal, as well as also in other densely populated cities, overcrowding at urban rail transit that become increasing concerns, especially with the population of the growing population in the urban areas, and it can lead to the discomfortableness of the users, can lead to the difficulties that in the safety operations, as well as the risks of the operational efficiency and on-time performance. So most of the time, from the operator's perspective, the simple solution is either they increase a higher frequency or they increase or they have a longer train, so increase the capacity. However, a variety of the system that it has an unknown factor, which is unclear of what will be the impacts of this increase of or the changes or adjustment of those services that in the passenger side. And existing literatures also suggested that passengers could have their flexibility and different preferences that for adjusting their schedules corresponding to the operator schedules. And some cities and some regions has implemented the peak hour surcharges, off-peak discounts, but the measurements and evaluations of those efficiencies, as well as what could be the pre-decisions of which strategy to be used, that is put in a place where it's unclear to the operators. So that is how drives us to develop an agent-based learning framework, which we would like to derive those dynamics of the passengers and also the real-time spatial temporal dynamics within the urban rail transit system. So the agent-based learning framework that comes first from the data input of the service, the travel demand, infrastructure, and network. And we aggregate the data from the individual level as well as the system level. So the individual levels that we are mainly getting from the smart car data, and the smart car data include tap in, tap out. And the system that we have tested the framework has both including the tap in, tap out. Some other system that may only have the tap in, that depending on how the urban rail transit system smart car data are designed. The system level data including the overall change of the origin destinations, as well as the annual increase of the origin destinations. Infrastructure data is more of the static data that including the links and nodes, and the service supply data or the operational record of the train frequencies, capacities, and also as well as their departure time. So this framework that we leverage 30 millions of records from the different regions and from different countries that to validate both its accuracy as well as the scalability. With this framework that we focus on the dynamic workflows, where we're looking into three key dynamic agents defined as agent that in the framework. The first one is traveler. So we consider every traveler as an independent agent, where the travelers will have a multiple status, including the pre-trip, walking to the platform, waiting at the platform, or transfer from one platform to the other platform until the actual arrival. Uniquely that in this framework, we also consider train vehicle and platform as agents from the perspective that although it's operated by the operator, so it's kind of a proxy of the operator's decisions, where the train vehicles will also have the capability where we will measure what will be the occupancy of the train that during, for example, during the morning peak hours or from different departure time service rounds. And then the platform will also have a dynamic status of the platform crowdedness that by the passengers across the peak or across the peak and off-peak hours. So this agent-based learning and also a framework will capture those simultaneous operation interactions between the traveler's train and also the platforms as overall. So from the beginning that in this agent-based learning, we do need to develop a simulation environment. So this simulation environment will include in the network environment and operations that we addressed what could be the line intersections when there are transfer stations and whether each line had a shared platforms or routings. As well as an input from for the train departure time and the records. So here picture A that we could see for a sample service runs that in a specific line, there is additional services added for each of for different stations during the morning peak period from 7 a.m. to 9 a.m. So these settings that serves as the interaction static foundations when we adding the dynamic agents that to our agent learning environment. Then if agents, for example, have a shared platform, they may have a shared crowdedness altogether as a cumulative characteristics. Then after those network settings and environment, each of the agent, the three types of agent will have a different status depending on what's the current time and what's the current locations that in the learning-based environment. So this is examples of when we are looking at the passenger agent, and this is a trajectory of how the passenger agent will going to change as long as this agent has been entering into the urban rail transit systems. And then at any time, at any location, the agent learning environment will have a composition of different agents at different status. So this is an abstract concept of when we have a platform that has a intersection lines, then we may have agents that are just walking to the platform or arriving or just living to the platform or waiting to transfer to another lines. So this indicates those dynamics of those different agents at different status in the agent-based learning environment. So we did a benchmark case studies with a Beijing metro network. We used a 2.3 million trips with a benchmark period covering from 5 to 12 p.m., 5 a.m., which is typically the whole morning period. The operational record we're using, the capacity design, we use 1,960 passengers per train, which is a standard capacity of a train that are used in the morning during this line. And the benchmark entry and working time for the passengers 90 seconds, exit time also 90 seconds. So we used the different levels of the data that from the smart card, including those entry date and exit date, destination origins, and also the operational record, including what are the train, each of the service ID, as well as their arrival time and departure time. So when the agent-based simulation start to run, and this simulation will run at exactly at 5 a.m. And for each of the 5 a.m., the simulation can be set with a discrete time updates from 5 seconds to 1 minute, depending on how accurate that we like to capture the dynamics of all the agent status that in the urban rail transit. So in this example that we show is the simulation will update every 20 seconds. And this is set that considering it has to be smaller or equal to the minimum dwelling time of the system. Because if it's greater than dwelling time, that we were going to miss, in some cases, a whole train boarding or the aligning events. So setting up the discrete train will be very important, especially considering the operational record. So there should be a consistency between the dwelling time and the discrete time updates. Then to update, we first will update the service run agent, we first will update the train agent. So every 20 seconds, we will update the status of the train. Then we update the status of passenger. And after that, we will update the status, how the passenger will enter into the train or staying at the platform. At the end, we'll provide a platform agent status on that. So this is the result of when we are running the whole morning period of the agent, and we will see the differences from upstream stations to the downstream stations. So from upstream station, which is on the right side, to the downstream station, the central, when we see all those like transfer symbols, is basically the downtown areas in Beijing. So the upstream stations are more residential areas, and the more that we are going across, the train that going across from the upstream stations to the downtown areas, then we see the increasing of the crowdedness in the platform that has been accumulated along the way. And particularly for this specific platform, that we see a sharp increase during the peak period, and also a critical crowdedness that in the central period. However, we are not sure yet at this current moment if this is true or not. It is simply the simulated environment, and it's simply the simulated result. And a variety of the key challenges for the agent-based simulation, and especially for just using the data directly, is the difficulties of how accuracy and how correctness this result will be. So we know that this station that is crowded, but however, if the operators want to address or have strategies or actions to reduce this crowdedness, how many trains they need to add, what could be the frequency that they need to add for that, and also how much that this train is overloaded during the peak period. And this drives to a very important question, is that how can we validate this result? And if this result are true or not? And that is what we are focusing on to learning to drive from a simulation or a static simulation, agent-based simulation to an agent-based learning that will provide us a dynamic and also a realistic characteristics of the systems or internal systems. So if we are keeping all our current settings of the agent-based simulation, and that is what would be the indicated waiting time for that station. So for this specific crowded station, with the benchmark result, it indicate the peak hour waiting time will be greater than 1 hour. That has a design capacity of 1,960. And this is not realistic and is also not aligning with what the observations that we had in the actual system there. So the key issue that drives to this result is that when we are just use directly the data, especially during the peak hours, the crowdedness can cause in the interactions of passengers. And each of the passengers and the simulation, when we set the design capacity of 1,960, that basically will cap the passengers to enter a specific train. And if passenger will not be able to, so if there is a denied boarding, which means passengers will not be able to enter a train because of overcrowding, they have to shift to the next train. So these characteristics is very can be a very sensitive parameters in deriving an accurate result from the agent-based simulation framework. So to derive a correct parameters and also to provide improve the fidelities of the result from the agent-based framework, we first do the validation of our framework mechanism. So this validation, we will compare the simulated arrival time with the tap out time of the passenger agent. This is a trajectory. So this picture shows a trajectory of passengers when they just enter in the system, what will be their status to get in the train and how long they wait in the platform and when they will exit the system. So each of the passenger agent will have these trajectories, and there are millions of the passenger agent in the systems, and that will provide us a rich comparison record that can help our validation. And next step will be the learning performance. So the validation will first come with off-peak, which is to validate the mechanism of the simulation environment. So the purpose for doing this is to separate the peak hour effects separate the peak hour effects with off-peak. So we will first only look at the off-peak that to ensure the mechanism of simulation is correct. This can including, for example, that our discrete time of days is set correctly, that is smaller or greater than dwelling time. Because if the discrete time is set up too large, that will induce also larger discrepancies of the simulated arrival time and also the tap out right time. So there are few extreme values when we are using that, and those few extreme values that we saw that in all the systems that we tested in the framework, and that can sometimes comes from more of the passengers which may not be a regular commuters, probably can be some of the regular staff or working people that are in the system. So those are the record that we actually need to eliminate it from our validation because they're not in the scope of validating our mechanism. And in the overall that this mechanism has showed, in this case that we have showed the matched result within 3 minutes that is falls within the tolerance range. Then after that, we are validated the mechanism with some of the parameter settings of the agent-based simulation. The next will be how can we derive what will be the ground truths, what will be the realistic parameters during the peak hours. And those will give the insights of how people behave differently when they're using the urban rail transit system in off-peak and peak hour, and how the operational characteristics are are performed differently. So that the direct insight would be what will be the overcrowdedness, what will be the over occupancy, and the quantification of over occupancy during the peak hours. So as I introduced that at the beginning, a key challenge is that in a lot of urban rail transit systems, especially in those crowded systems, although operators are aiming to improve their performance and trying to reduce the crowding, especially due to the safety concerns, it's still unknown of what will be the passenger in-vehicle loading and occupancy. We have input and output of the data from the system. Like, for example, smart card tapping, we know how many people are tapping every day for each of the station. We also know how many people are tap out every day for each of the station. But how those system and how those each of the passengers are traveling that in the system and how the system dynamics of crowding is an unknown parameters for the operators. And also that this will make the challenges and difficulty for operator to decide what could be the optimal capacity and operations. And the agent-based learning framework that we derived is tackling this kind of challenges. So we use the cross validations that between the simulated arrival time and also the smart card arrival time. And here shows the comparisons. So this picture shows the comparisons of if we set a different working time, access time, as well as the train occupancy time, then how these discrepancies, how the validation record is going to change. And we see during the peak hour, which is the pink areas here, we see a large discrepancies during the peak hours for the same for the same occupancy record. And then the off-peak hour will be smaller discrepancies. So the y-axis shows how much the discrepancies, what is the differences of the simulated arrival time, and also the actual tap out arrival time by the passengers. So there are two steps. This is a two-stage validation. The first stage is that we do need to first validate the off-peak hour first by eliminating the overcrowding effects. So the off-peak hour validation are driven from the calibration of the working time by the passengers. So recall that our preliminary working time is 90 seconds for both entering and exiting the stations. But however, after we validate that, we actually find out 70 seconds as a working time in peak hour and 50 seconds as working time in off-peak hour is what is the actual passengers' behavior that in these urban rail transit systems. And by adapting this working time, the next stage is to calibrating the overcrowding. So calibrating the overcrowding is what will be the actual occupancy of the vehicles. So original record showing that original design capacity of the vehicle is 1,960. But however, when we are validating it through the calibration, the actual occupancy that passenger are entering the train is 2,300. So this actually indicating 340 more boarding than what's the design capacity. And that gives a quantification for the operators of how much and what is the percentage of overloading this system and this specific line is. And the operational through the operational record when we're comparing with operators, and that indicate a peak overloading of 13% to 14%. And once we validated that, so passengers crowd and queuing patterns will also be corrected to a realistic pattern. And this actually indicated another important aspect is utilizing the data in a validated form, not only just for the quantification, but also for a pattern recognition. So when we are using a design capacity of 1,960, our weighting patterns is totally different when we are using the actual and realistic occupancy. And that's actually if we are just using a wrong information that will drive um, a more worse conditions that in the transit systems. So if so from the derived, if we look at the left side, if we're using a derived the wrong derived result, then we actually will put more, we probably the operators may put more frequencies or more trains that's at the shoulder peak period, which is not actually the actual peak period in the urban rail transit systems. And we further also validated for understanding what will be the actual passengers' routine behaviors when they're using the urban rail transit systems. And this is comparisons of how much deviations that we were going to get if we are using a different categories of passenger routing criteria to understand their behavior. And if we assume passengers are choosing shortest dynamic travel time, and this is the comparisons of our simulated result and also their actual tap out. If we assume passenger are choosing the least number of stops, then we will see a higher discrepancies for the simulated result compared with the simulated result with the tap out result. So in this system, with this system, what we can see is that passengers are actually choosing the shortest dynamic. They're choosing more. They're choosing their routine based on the shortest dynamic travel time. In the other system, we do see some differences. So for some systems, passenger will more prefer to choose the least number of stops. So this reflecting a specific systems, what are the passengers' behaviors and patterns when they're using the urban rail transit system. And that gives also another dimension of how the system should be designed and from the long-term planning and investment perspective. Um, so, so far that we talked about the agent-based simulations that in the way of how can we use the multiple record and also the different self. So this type of the approach we actually use more of a self-validation. Is we use the tap out as our validation to compare with the simulated results from the tap-in data of the smart card. So we don't require, so this type of is kind of a closed loop that we don't really require other external references or some other manually checking to cross-validate. So this self-validation will help and provide a closed loop of the method, which all the data are readily available generally from the operators systems if they have a tap in, tap out system. For some of the urban rail transit system, they may not have a tap out system, but they probably will also, but for some systems will also have the survey data or a sparse or some of the sample data of the passengers track record as well as their census data, which can also be used in the same framework of how we are validating and calibrating the actual occupancy or the actual working time for the passengers. Then those results are showing an aggregated level, is showing of, if we look at the system briefly of what could be the approximated actual working time and capacity. The next that opens, so this also opens, especially when we are treated each passenger and vehicle as agent, it opens the learning opportunities where we can disaggregate all the passengers and all the trains by assuming that they actually will have their own preferences and their own preferred working time, as well as the occupancy for each of the service rounds. And in here that we developed the reinforcement learning method. And with the reward function that we still are calculating the differences between the simulated time, simulated arrival time and the tap out arrival time, plus the crowding that in the vehicles, as well as we added a stability penalty for each of the learning steps. If there is large gaps if there is a large differences between the previous learning epoch and then the current learning epoch, then there will be a higher penalty. So this is to increase the stabilities of the learning, and we will see how the learning is converged to a stable environment. And for a disaggregated learning perspective, that if operators would like to know more specifically whether there will be the differences between each of the stations, and that is how the learning and it's disaggregated learning will provide for different stations the access working time and egress time that can be different depending on it can be depending on the passenger's social demographic and also depending on the passengers or depending on the land use or land planning that in that regions. So here we see how varies the working time. In some of stations, passenger will more take like 55 seconds of working time. Some stations like 30 seconds of working time. That's also reflected based on that can also be reflected based on the station design as well. So the result and the comparisons validation that provide the insights of how we could use a multi-source of the data as well as a self-validated method to provide a realistic and also an operational characteristic to the operators. On the other perspective, that when we are using this type of method, the passengers and especially in the urban rail transit, the demand is dynamic every day. And also, if there are disruptions or if there are any of the maintenance happening, then the demand can change as well. So this system usually also requires the real-time or nearly real-time or fast result output rather than offline system. So scalability will be one of the important part that we should consider. So we use the speed up techniques where that we first ground the trips by the origin destination pairs. Then we are looking into what will be a specific passengers' route preferences and choices. And we tested the scale of those agent-based learning and simulation from 500,000 trips to 3 million trips. And for a 7-hour simulation, 7-hour output, we will get it from 10 to 30 minutes, which is at a tolerable scale. But this provide of how scalable and what will be the change of the timing of those the agent-based learning system. And overall, that this the learning system provides the dynamics of the real-time interactions as well as a validation and scalability method of how can we use the multi-source of the record. Then these cases provide the inference application perspective of how we use the data. The next case I would like to introduce is about infrastructure multi-sensing for the rail track. This is another also in the transportation areas, also in the railway areas, that some of the method has been deployed and some of the method has been tested or piloted. The difference between the inferences and also the multi-sensing is that inferences studies are usually using the operational record or the smart card, which those are typically reflecting the actual record. But multi-sensing data usually include a lot of noises, and these noises indicate the errors, and those errors has to be deleted from the system. While in the inferences, we are not really seeing much of the errors, but it's more of driven from behavioral perspective. So multi-sensing systems, one of the studies that we did is to measuring the rail track gauge. And this is we use the data collected from the LiDAR sensors and also from the GPU sensors. And the key challenges that we need to do here is that it's a high noise data. So a majority of the sensing data is high noisy, and that's that requires to develop a high fidelity method. So this should come from 3 perspectives to address this high fidelity in high noise. The first is a transformation system that should help us from the physical sensing system to an actual earth sensing system. And the second is that we should develop a processing and clustering method, which will aggregate and help us to differentiate what are the noise data, what are the error data, what are the actual usable data that we're using. And finally, is a refinement of our measurement. So this specific data is for a specific study is for the gauge measurement using the LiDAR. So the transformation system is how can we transform the LiDAR system to an Earth system that is understandable and interpretable. So this is all related to how we can transfer physically and what is the angles of from the LiDAR system to the Earth system. Then after we transform it to the Earth system, we'll be able to show and we'll be able to have a correct of the patterns for the different shapes of the tracks as well as the geometry of the tracks. But we can also see that all those like single points that are listed here are all the arrow points, and they can be affected by maybe by my vegetations that in the railway tracks, or can be affected by the sensor hardware itself. So it is important that we first need to we need to identify what are the actual scans from a pool of the noisy data. The ideal scan should show a clear shape of the track. However, the actual data is all noisy, and if we identify the age of the scan that in the incorrect way, that can cause an underestimate or overestimate of the track gauge. And more specifically, so from this, we implemented a clustering algorithm where we actually are clustering different patterns of those scan point um, by its own density. So in here, we can see the different colors of those scan point, which showing the different patterns of those scanning point. Some of the noise data are clustered together, becomes a one cluster, and that is a cluster we can identify. We can drop it in our later. So from this way, that we actually aggregate those noise data in a cluster, and then drop it from its actual from the real scan. So after we'll be able to drop those data, arrow data from its clustering by batches, then we will use the geometry of the track to identify what could be the accurate pair to measure the gauge. And further, we rank this pair. We will rank this pair to understand what is the most accurate gauge measurement that's in this track. So with this spatial density oriented gauge measurement algorithm, finally we compared a different method together, and through this process, that first identifying and clustering the noise data to integrating the geometry, that we can improve 60% to 70% of the gauge measurement accuracy. So the measurement, so when referring to the infrastructure multi-sensing, one important thing is how we are merging and mapping the data to the actual track. So in this case, is a gauge measurement, then how can we mapping the key components? How can we mapping the sensing data to the track gauge geometry? And in here, that we also will involving the tuning as well as the domain knowledge that to help us to understand, for example, when we are designing our clustering algorithms, we have to understand what could be the density tolerance for the noise data as well as for the gauge scan, and also that for the different geometry, if it's a crossing, level crossing with turnovers of straight, that our density, spatial density algorithm should address all of them. And with our algorithm, we will be able to address them automatically by properly training and tuning those parameters that we developed here. So the third case that are referring to, so we talked about the inferences of how we use the data, how we use the first primary data to address our secondary or derive our secondary insights. And the second case that is more for the measurement of what kind of key key clustering algorithms that we developed by addressing the geometry, integrated geometry with multi-sensing. And the third one that I'd like to introduce is a condemnable failure predictions for the rail wheels. And this is addressing the prediction direction of how we are using the data. And this is referring also to the time series prediction. So to the condemnable failure prediction and this type of the studies, the key point is that we have a historical data from all different sensors or the record. So in these studies that we are using, for example, the wheel profile, wheel impact, trunk counting, mileage, or vehicle metadata, or failure logs, all these are the historical record. What we need to do, the task is that we are going to predict the failure and what is the probability of the failure within the next 30 days. So these prediction tasks involving first, how can we aggregate the data? And how can we intercorrelate the data? Can we use the cross-validation between the data sets, which can help us understand better the trend of the failure of each of the wheel? And more importantly, to address the short-term and the long-term trend, so that we will be able to capture both the random failure as well as some of the defects caused by the operations. So this study is one of the competition winner studies that we have also worked with Informs and TTX in last year. So real wheels and those type of the data that we collected from both from different sources. The key challenge is the sensing. So all those data are actually collected from different equipment, not from different manufacturers. So the data is collected at multi-rate. Therefore, that all our data that has irregular sampling. So some data may have a history record of 7 years, but some data may have only history record of 5 years. And the missing record, a rate of missing record is also very important. So normalizations and uniform of those multi-source data will be very important. Then there are outliers or domain invalid values where we need to address for each of the different data so that we will be able to integrate them together. The failure data also have severe class imbalance. We only find 1 to 2% of the failures. And we also need to avoid the overwhelming or the impacts of the zeros values to the 1 values, which is the failure values. So data topology, including the different scales from the axles levels of the data to the vehicle level of data, such as mileage. And we're using about 20 million of scale of data that to predict this wheelset failure. And the procedures come from, first we'll do all the cleaning for each of the data set, and then we are processing it based on its short-term and long-term trending to calibrate and also approximate the data or interpolate the data in a standardized form. After that, we do the aggregation. So we first do the interpolation, and then we do the aggregation, and that final that we do the model training and tuning. Key point when we're doing the cleaning and processing is that first, with the same data issues, that we might need to have the different handling procedures. So in the mileage data, when we have the non-values, then we usually will set non-values at 0. But however, then in the WPD dataset, if it's non-values, we have to remove those non-values because setting 0 actually means giving means that some of those flange is 0 or gradient is 0, so which is not correct. So even with the same data issue for different data set, it will have different handling. It has to have different handling process. On the other side, for the different data set that it may have some unique data issues and need to be customized. Like failure data sets sometimes will have duplicate information, while mileage data set will have negative values. So these are the two different layers of how we should process the data properly, that to make it efficiently for our next training. And this will require both the integration of data techniques, and the domain knowledge. Then we tested the data. Once we process all the data properly, we test the data with short-term interpolation and the long-term interpolation. So short-term interpolation reflecting more of how this wheel set has been used. It can be affected by the mileage, can be affected by the loading, can be affected by the operation. Long-term interpolation, in some cases, will reflect the manufacturing defect, reflect its lifespans. So these are the two different perspectives where we both need to address when we want to predict the failures, because a failure can cause both by its operational usage, but also by its manufacturing defects or manufacturing differences. And there will also be a gap of how there will be a threshold of how good our prediction will be depending on what type of usage, what type of the data that you're going to have. So for the failure perspective of the data, most of data are have the time series perspective. So tree-based model or gradient-based models has better performance than neural network because it addresses those sequential consequences of the failures that in the wheel set rather than the neural network. And that is what we will see also in our result. So here is a glance of when we try the different Fourier transformations or the long-term or the low-pass FFT low-pass transformation, how this for different filtering or sensing filtering, this is a performance of a different method, and we usually pick the first two or three as our best choices. Then as for when we are processing the short-term, long-term, that will provide us a data interpolation. So now we will have interpolated data, smooth data, continuous data, which will be ready for a model training. And this model training, we consider this as two categories. One is gradient tree-based category, another is neural network category. And with the gradient-based category, this is to address extreme polarized 0-1 data. So the first will be a feature level importance that will help us to remove all the unnecessary data and focus on those key features that are going to affect the failures, as well as a performance matrix selection, which will also, we use the macro average F1 or log loss. This reflects the overall accuracy rather than the recall or precisions. So with the data handling, we also tested the differences of when we handle the data through our method and without handle the data through our method. And we can see the macro F1 has increased 20 to 30% once we have processed and also interpolated the data compared with aggregate if we just use the pool data or aggregated data. And here shows the final result of when we are testing all different models, and also we compare the models with the parameters tuning. Light GBM has the highest performance, also had the lowest performance. So this indicates that when we are evaluating the failure or the prediction related tasks, hyper tuning and parameter tuning can make a greater effect. And when we are properly tuning the light GBM, that becomes the highest performance that in our prediction. And then on the other side, we also will be able to see that the top performed algorithms, they're all either time series or gradient boost or tree boost, which including or involving the historical information to their algorithm or to the algorithm predictions, they perform better than MLPs or CNNs, which are the neural network. So categorical wise, from efficiency and effectiveness, the matching between the data properties and also the algorithm selections can also will also make impacts on our performance and also the result. So that comes to the end of my seminars. So from a broad glance of view, that some of the experience or lessons that we learned, one at inference, if we are inferencing the secondary characteristics from utilizing the data, for example, the urban rail transit overcrowding or train occupancy, validation of the parameters will be very important, especially although the system has a design parameter, but the actual parameters that are used by the users or are implementing the system can be different or quite different than what is a design parameter will be. So using the design parameter can causing a large discrepancies or be a wrong information to the operators. Uncertainty is another category of the variations as we see when we are adopting the agent learning, then the egress time and egress time, working time for each of the station can vary a lot. For some of the station, even there with a similar design or with a similar operational record, that passengers' behavior can be different. So uncertainties with the agent learning and especially with the current agentic AI, as well as the individual level of the data record, that can help us to address those variations and uncertainties. There are also balance between the quantifications as well as the qualifications, depending on. So when we are looking to for the case that we're looking to overcrowding, the aggregated level of what is average crowding, the system can give operators insights on whether they would like to more increase the frequency or they like to increase the train capacities, and that adjusts them what kind of strategy or policy they can use. From the measurement perspective, the data is different, where this is more of the balance of how we're going to address errors of the data, and the processing, the automations of collecting those multi-sensing data will induce repeated errors. So the errors will also have this pattern, which allows us to use some of the AI mechanisms such as clustering, such as the classifications. So we will be able to aggregate or disaggregate the errors from our actual data. Also, the sensor sensitivity and data richness, there is a balance. At the end, that for some of the studies we do, maybe only 30 to 40% of data are usable. So in some cases, it's also not that necessary to use all the data. What is really important is that what kind of information we need to have and how we can process to get that information between the amount of the data and the useful information we can get from the data. And if we don't really have a good data quality, then we can compensate with algorithm models at what we did in our case 2, where we actually compensating, we develop those algorithms which are compensating the quality of the data. Prediction tasks usually addressing the extreme imbalance data, and there is a trade-offs between the performance and data processing effort. The data processing can be endless, and there are numerous ways of how we process the data. But our experience is that usually it could have a threshold where that there are some boundaries. At some point, it won't make too much it won't make too much improvement with further processing. So it is important to recognize like when and where that we should stop the data processing, and at some point that this processing results are enough to proceed with the model training. And in the processing, like domain knowledge will be very important to be involved, but model training perspective, not necessarily. That is what our experience that we have. And also that is important to be aware of the information leakage. So for example, in the wheelset, that we probably have a historical record of this manufacturing of what is the lifetime of these wheels, but those actually are not suitable to be using the data because that reveals the information leakage. it will drive a better performance, but that is more of the performance hallucinations, which is actually not reflecting the actual predictions. So those studies are we would like to acknowledge our sponsors and also our partnerships that supporting these studies, and I'm happy to take any questions.
Dr. Tang, that was amazing. Thank you for the presentation. Really appreciate you taking time to give this seminar today. I think we'll go through the questions in sequential order. It looks like we have two questions about your first case study, one question about the second one, and I know I have a couple of questions about the third one if no other folks type them in. But for the attendees, please use the Q&A tab and you can continue to enter questions. So, and Kelly, I'm not sure if you're looking at them as well, but we'll start from the top.
Sure.
For case study one, can you share which simulation tool is used for the agent-based modeling, and would it be possible to make it available to other researchers?
Thanks. That's a good question. So we actually developed this agent-based framework by ourselves, and we will make it open source. We will make it open source. So the study has been published in the Journal of Rail Planning and Management. So the paper will be available soon, and the open source package will also be available soon later this summer.
That's great. Then the second question regarding the first case study relates to kind of passenger behavior topics. So, how do you simulate passenger trajectories? Do you assume passengers follow the shortest path? And how do you address passenger route choice issues during peak hours with overcrowding?
Yeah, that's a very good question as well. This is also one of the rationale that when we are developing this validated framework, so we need to have a concrete references of what passenger like what the preference of passenger route choices, and from for example that in and through the validated framework, we actually will be able to know what will be the appropriate criteria to choose. And that need to go through assessment. So, for example, in here, this system that we use in the Beijing Metro, passenger is more prefer like is more tend to choose the shortest dynamic travel time, and that what we see from the validation result.
That's great. All right. Question. We'll move on to case study two. Let's talk about the specific question here about resolution on your LiDAR gauge measurement.
So the LiDAR that we're using is 100 hertz that we're collecting a frequency 100 hertz. So it's actually not in a very high. So it's a very affordable LiDAR. So the cost is like about several hundreds. That also drives us how can we develop an algorithm to address this when we compensating with the data availability.
That's helpful. I guess I've got one more question on that one too. When you're the field of view of your LiDAR that you're capturing, are there other useful reference frames that you've tried using to eliminate areas of noise or real data, like the straight base of the rail or things like that? I couldn't tell if we were looking at kind of localized snips of data that were close to the head of the rail, or you have more data around that to parse out real data versus noise, I don't know if that makes sense.
Yeah, so do you mean that if we are using, let's say, the image data or
No, I mean using your LiDAR data, there's areas where you have the clustering of noise
yep.
to be able to identify it as noise. Are there other reference frames that you get in your raw LiDAR data that would inform you the likelihood of that being noise to improve the clustering algorithm? I don't know if that makes sense, like the straight base of the rail and reference of the clusters to that and knowing whether it's in space or on the surface of the rail. I don't know if that makes sense.
Oh yeah, I see. Yes. So we will be able to, so the cluster algorithm will be able to identify. So for example, in this picture, we can see, I think I will show maybe here. So in this
Okay.
picture that we can see that those green ones are clustered together as one cluster.
Yep. Okay.
Um, yeah, and then the red ones are clustered and another. So we actually dropped the green ones. because these are not in our
Uh,
scan field. And we use the geometry. So yeah, we use the geometry information of the railhead. So for example, the height of the railhead and also the width of the railhead. So that can give us concentrated. So this bounding box
right.
is a concentrated areas.
Yeah, that's what I was getting at. Thank you. It's a
Yeah.
good clarification. Um, we'll move on to case study 3, and one question has come in regarding that. Are the North American Class 1 railroads aware of this case study 3 work? And if so, what's their level of interest?
Yeah, that's a good question. Yes, they do. So we actually had discussions with a couple of real class one railroad because especially that for the wheel profile detectors and all those detectors data. Um, I think several of the class one rails that may already have their own in-house equipped facilities there. And those data are in large volumes and large profiles. And we're also working on this one of the our current ongoing and also future is to how can we scale it up and also make it transferable. The good thing is that typically those data are in a standard form and shape structure. So structure-wise, that it makes it possible that to be a transferable framework. And we are also working on open source. The method that or pipeline that we developed, and that will be made available later as well.
That's great, Kelly. I enjoyed all 3 case studies. I'm especially interested in the possibilities for case study 3. And I was going to ask you, when you look at the data set that you have, I know you talked about its size in terms of millions of points. What is kind of when you look at all these raw data sources, what is the time frame that you cover in terms of the length of your data set, the union of this in the event that they're at different time frames?
Yeah, yeah. So there are 7 years of the record.
Okay.
Yeah, so the data set is 7 years of record, and then we use it for predicted for the next 30 days.
Okay. I
So
follow.
when we did some of the arrangement of the time frame. So like we include the short term and also long term. So the whole data set is like 7 years. That's reflecting what the long term trend. But also for the short term, we use the past 3 months as a short term. So that's reflecting the short-term processing and their patterns of how it's used. Because some wheel set can be used very heavily in the past 3 months by short term, and sometimes that may causing extra stress on the wheel set.
That makes sense. I guess, do you have any comments? We we here also spend time cleaning data, and I appreciate your slide where you talked about a lot of the organizational work that has to take place before you can apply some of the AI approaches. When you look at these data sources that are up here on the screen, again, you indicated that you have to treat them all differently for good reasons and do different treatments. Which ones are the easiest to work with, and which are the most challenging in terms of the manipulation of the data to even begin using it?
Yeah, that's a good question. So we treat the data we treat the data as two categories now. Like we are more looking into the data in a processing perspective is that um, so we first identify what are the data issues from all the data set. Because for example, this is example of these two data sets. They have data issues of non-values, negative values, missing information, on that unidentified information, and duplicate information. These are the 5 categories of data issues. Then we map these data issues to the data set. So in this case, that will give us, if we are going to have a different handling for the same data issues. After we did this batch, then we were looking at the unique data issues. So actually, when we aggregated the data issues, that can solve, I would say, like 60 to 70% of the work.
Okay.
And then the remaining would be those unique data issues. So
Okay.
we find that that could be an effective and efficient way to reduce those like processing time rather than looking each of the data set individually. So we pull the data set first and look at the data issues first.
That's great. That's a clear explanation. Thank you.
Yeah.
If there no other questions. I want to thank you again on behalf of all of us here at Railtech and all the attendees today. We had a great turnout. Thank you for an amazing seminar. Kelly, we really appreciate it. And for everybody online, we'll restart again for the fall semester with some in-person and some maybe some virtual seminars as well. And Kelly, thank you again. Have a wonderful weekend and thanks so much. Great seminar.
Thank you. Thank you so much. And thanks, Realtech, for having me. And it's great to see everyone and happy to discuss further if there are any questions.